Hi, I'm presenting LOL, longer than longer, scaling video generation to the hour scale. Autoregressive streaming with attention sinks pushes long video to the minute scale, but it suffers from a hidden failure where the model snaps back to its first frames. We diagnose this as a multi-head synchronization problem in rotary position embedding, and fix it with a tiny training-free trick called multi-head rope jitter. The result is, to our knowledge, the first real-time streaming generation up to 12 continuous hours. Recent, ultra-long video models, long-live and self-forcing ++, push streaming to the minute scale by keeping the first few frames as attention sinks. These sinks stabilize generation, but at long horizons, the L2 distance to those sync frames drops sharply at very specific indices, like 132 and 201. At those points, the video abruptly snaps back to its start. We call this sync collapse. Strikingly, it happens at the same indices regardless of prompt or noise seed, which tells us the cause is structural. Why does it happen at those specific indices? Two interacting properties. First, rotary position embedding is periodic, so at long horizons, multiple temporal frequencies realign with the sync frames. Prior fixes such as Rifflex blame a single dimension, but we show that perturbing any single rope dimension does not remove the collapse. Second, on collapse frames, the attention maps show many heads spiking on the syncs together. So sync collapse is not one bad dimension or one bad head. It is a collective synchronization across the multi-head subspaces. Our fix follows directly from this diagnosis. For every attention head, we perturb the ropey base frequency by an independent random factor, theta hat for head h, equals theta 0 times the quantity 1 plus sigma times epsilon h, with epsilon h uniform on -1 to 1. Intuitively, if every head ticks on the same positional clock, they all realign with the sync at the same moment. Giving each head its own clock keeps ropey's relative position behavior, while making simultaneous spikes on the syncs unlikely. It is training-free, model-agnostic, and drops into long-live and self-forcing ++ unchanged. With collapse removed, three pieces take us to the hour scale. The backbone uses local attention over the most recent n latent frames, so compute per step does not grow with video length. The underlying WAN model uses a 3D causal VAE, enabling sliding window decoding at constant memory, and we sample rope positions and initial noise online, removing the fixed sequence length budget that previously capped these models near 4 minutes. Together, this turns a few-minute horizon into continuous hour-scale streaming on a single H100. Here is the main quantitative picture on 100-second long-lived videos. Lower sync collapse is better, higher dynamic degree means stronger motion. Direct extrapolation collapses badly. Position interpolation and yarn do suppress collapse, but they almost freeze the video. Rifflex, designed for bidirectional models, behaves like extrapolation here. LOL is the only method that pushes sync collapse max from 73 down to 17, while matching the dynamic degree of the original model. That is a 4.4 times reduction in collapse, with essentially no loss of motion, and 12 hours of stable streaming in our demos. The ablations support the diagnosis. On the left, we sweep the jitter strength sigma. Small values leave clear L2 dips. Those are sync collapse events. Around sigma equals 0.8, the dips essentially disappear while quality stays stable. On the right, we vary the fraction of attention heads that are jittered. As more heads are perturbed, the curve flattens and the dips shrink. Exactly the pattern expected if collapse is a collective effect. Single dimension or single base changes, by contrast, only shift the failure in time. To wrap up, we identify sync collapse as a major bottleneck for ultra-long autoregressive video generation, trace it to multi-head synchronization under periodic ROPE, and fix it with a lightweight per-head jitter. No extra training required. Combined with online ROPE and noise sampling, this gives the first real-time streaming generation up to 12 hours with little quality decay on a 1.3 billion parameter model. Future work: true long-term memory, stronger base models, and richer control signals. Thanks for watching. Come find us at the poster.